So, last class I have discussed about different shear failures and then the Tazaki's bearing capacity equation, and then how we can use the Tazaki bearing capacity equation for local shear failure, because originally it is developed for general shear failure. Now, today I will discuss the other bearing capacity equation. So, first I will discuss about the Mehrab bearing capacity equation, then Hansen basic, and then the IS code recommendations. So, the second bearing capacity equation, before that I have also discussed the Skempton bearing capacity equation, but that is applicable only for clay soil, and Tazaki's bearing capacity equation can be applicable for clay as well as sandy soil and C5 soil. So, but in Tazaki's bearing capacity equation, the load is considered perfectly vertical and there is no eccentricity. That means, load is acting at the center of the footing, but sometimes footing can be load can be eccentric as well as can be inclined. So, those there is no provision to include those effect into the Tazaki's bearing capacity equation, but and then the Mehrab has developed a bearing capacity equation where we can include these options. That means, we can include the effect of inclined load, we can include the effect of eccentricity into the bearing capacity equation. In addition to that, in Mehrab bearing capacity equation, we can include the shape effect of the footing, we can include the depth effect of the footing also. So, this is the Mehrab bearing capacity equation, where this is a general type of equation, because in next bearing capacity theories like Henson, then basic and IS code, the equation is more or less similar type. So, this equation CNC similar to the C is the cohesion of the soil, NC is the bearing capacity factor, then Q0 is the gamma into DF, and NQ is also bearing capacity factor, N gamma is also bearing capacity factor, B is the width of the foundation. But here SC, DC, IC or AS, DI, these are different factors. So, AS is the shape factor, D is the depth factor, and I is the inclination factor. So, that means originally these equations are developed for the surface footing. So, if you have a footing with a depth, then you can incorporate that depth effect into this bearing capacity equation. So, and as I mentioned, then the inclination, if the loading is inclined and different shape of footing, like your rectangular footing with different L by B ratio, then the square footing, and also you can include the eccentricity of the loading, that I will discuss in later part of this course, that how we can include the eccentricity of the loading in detail. So, these are the factors, but here the bearing capacity factors NC, NQ, N gamma values are given corresponding to different phi values 0 to 50 degrees. These are the values. This is similar to the Tazaki's bearing capacity factors, those are also, but values are different, because but these are bearing capacity factor, but these factors are coming from this equation, those are given here NC, NQ, N gamma, and obviously these equations are originally developed for strip footing. So, for strip footing this shape factor, all the shape factors are 0. So, this is the bearing capacity equation for Mehrab, and so these factors can be calculated from this table. The shape factors for any phi value SC can be calculated by using these equations. So, you can use these tables to determine the shape factor, depth factor. I am just explaining that if it is NQ N gamma, then we can use this expression where Kp is the tan square 45 degree plus phi by 2. Phi is the friction angle of the soil, and similarly for SQ, S gamma is equal to 1 if phi is equal to 0 degree. Similarly, we can calculate the depth factor also. dF is the depth of the foundation, B is the width of the foundation, and again for phi equal to 0, dq d gamma is equal to 1, and dc is for any phi, but dq and d gamma if phi is greater than 0, 10 degree. So, either you will get the phi is equal to 0 degree or phi is greater than 10 degree. Most of the cases either it is a cohesive soil, that means your phi is equal to 0, or if it is a C phi soil, then if phi value is greater than 10 degree, then we can use these expressions. And then for inclination factor, this is the R is the load which is inclined, and this R has two components, obviously one is vertical component V and another is horizontal component H. So, and then sorry. Okay. So, two components, and this alpha is the angle which is making this R with vertical axis or the vertical load. So, that means here alpha IC and IQ will get from this equation, and I gamma will get from this equation if phi is greater than equal to 0. If phi is equal to 0, then I gamma will be 0 for any for alpha equal to greater than 0. So, alpha is the angle of resultant R measured from the vertical. Remember that alpha is measured from the vertical. Now, as I mentioned that in this equation we can incorporate the footing eccentricity also, but you just note this two lines where it is written that in case of eccentric loading, one can directly use Meyer-Hof equation with B dash and L dash to compute the shape and depth factor, and B dash in the term half gamma B dash n gamma. So, what does it mean? That as I mentioned, I will discuss this in eccentric loading effect in detail, but when you will what happened due to the eccentric loading, because now loading is not acting at the center of the footing. So, loading is acting outside the center of the footing. So, the effective area of the footing is now not B into L. So, because as the loading is not acting in the center, it is acting in away from the center. So, our effective area of the loading will also decrease. So, now the width will not be B, width will be B dash, because B dash is the effective width in case of eccentric loading, and L dash is the effective length in case of your eccentric loading. So, depending upon which way the eccentricity is, if it is in L direction or it is in B or width direction, or if it is in both the directions. So, based on that we have to determine the effective width and effective length, and then we have to use we have to calculate the effective area also. So, that means now in case of eccentric loading, when we calculate this shape factor and depth factor as per in Meyer-Hof equation, that means we will not use B or L, we will use B dash and L dash. So, how we will calculate the B dash and L dash, those things will be discussed later on, but now you remember that eccentric loading you have to calculate B dash, L dash, and that B dash and L dash we have to replace in B and L. Okay. So, that means the B or L or both are to be replaced by B dash or L dash or by both in case of eccentric loading during calculation of shape factor and depth factor as per Meyer-Hof equation. Clear? So, now another thing is that here in the third term there is a term B. So, in case of eccentric loading we have to take not B, we have to take B dash. Okay. So, these you have to remember. So, these two lines are very important. So, every theory is right now I will give this note, and later on I will discuss how these things can be used. So, remember that when you in case of eccentric loading, when you compute shape factor and depth factor, you use B dash and L dash, that means effective width and effective length, and in terms of B, in the third term of the equation you use B dash. Okay. So, next one, the Hansen bearing capacity theory. So, it is observed that the cohesive soil Hansen theory gives better correlations than the Tazaki's equation. So, this is the similar type of equation, as I mentioned, this is a general type of equation. So, the Hansen bearing capacity theory is this is the general equation, and the NC and NQ values are same as Mayerhof, but n gamma value is different. So, that n gamma value is given in this table, and remember that for phi equal to 0, this is the equation. Okay. So, phi equal to 0, this will be the equation, because NC 1 plus SC plus DC minus IC plus Q. Okay. So, in previous equation it is Q0 is mentioned, here it is Q, but both the cases either it is Q or Q0, it is gamma into DF, that means that surcharge. So, now here we can determine the shape factor, depth factor and inclination factor as per the Hansen's bearing capacity equation. So, shape factor you can use by this equation. Now, if SC equal to 0.2 B by L for phi equal to 0, for phi greater than 0, we will use this equation. Okay. Similarly, we can calculate SQ and S gamma, and remember that the S gamma should be always more than 0.6. So, if S gamma is coming say less than 0.6, then we have to use 0.6, remember that. If it is coming more than 0.6, then the actual value we have to use, but if it is coming less than 0.6, then we have to use 0.6. And for DC, if phi equal to 0, then 0.4 into K. What is K? K is dF by B, if dF by B less than equal to 1, and if it is greater than 1, then K is equal to tan inverse dF by B, and remember that K is in radian. Okay. And similarly, dq also we can calculate by using these expressions. Similarly, we can calculate K if it dF by B less than 1, and if dF by B greater than 1, less than equal to 1 or greater than 1. Based on that, we have to select the K similar to DC, and d gamma is always 1 for any phi value. Now, this is the inclination factor, we will calculate the inclination factor. So, inclination factor IC, IQ we will get by using these equation, IQ, NQ I will get from the chart, because NQ is similar to the Mayerhof NQ. So, from that chart we can get the NQ value, and similarly here also NC, NQ also we will get from the chart, because NC and NQ both are same as suggested by Mayerhof. So, and this is if phi is greater than 0 degree, and then IC will be this equation if phi is equal to 0 degree, where H is the horizontal component of the inclined load, because inclined load has two components, one is vertical, one is horizontal. So, H is the horizontal component of the inclined load, and then IQ can be determined by using these expression, and I gamma also can be determined by these expression, and here two I gamma equation is given. Now, first I gamma equation, if foundation base is not tilted. Suppose if foundation base is tilted, because there is a tilt, suppose if the foundation base, this is my foundation, okay. So, this is a foundation and this is the surface, and this is the surface, and this foundation is tilted. Suppose it is angle of eta. So, that means the foundation base is not perfectly horizontal. So, first I gamma expression we can use is foundation base is horizontal, but second I gamma equation we will use if foundation has tilted base with a angle eta. Okay. So, that we remember that. So, these are the difference between two I gamma. So, second one we will use for if foundation has tilted base, that means foundation is not perfectly horizontal, foundation has a tilt. Okay. So, if the tilt is there, then we will use this equation. So, later on I will discuss detail about the tilted base foundation. So, in that time we will use the second I gamma expression. And then few things you have to note that one, that there is a term A dash. So, A dash is the effective area. So, if your loading is not eccentric, then obviously A will be equal to A dash. A dash is the effective area, B dash is the effective width, L dash is the effective length. So, if loading is acting perfectly at the center, then A will be equal to A dash, or B will be equal to B dash, or L will be equal to L dash. But if there is eccentricity, then you have to calculate the A dash, L dash, B dash, and then we have to calculate the A dash. A dash will be obviously will be equal to B dash into L dash. Okay. So, that A dash we have to use. And there is a come Ca. If there is a cohesion is there in the soil, then Ca basically the adhesion. Okay. So, that adhesion I can calculate, multiply adhesion factor 0.621 times the base cohesion. Suppose base cohesion has a value of 20 kPa. So, the Ca value will be, if I take in between 0.621, that means 0.7 say. So, that means the Ca will be 0.7 times of that cohesion 20. So, that will be 14. So, Ca value will be 14 if I take addition factor is 0.7 and the cohesion value is 20 kPa. So, that Ca value will be 14 kPa. So, you can take any value in between 0.6 to 1. If it is anything mentioned in the question, then you have to use that value. Otherwise, during design, you can use any value in between 0.6 to 1 times the base cohesion, the cohesion which is acting at the base of the footing. Because another one is, as mentioned, H is the horizontal component of the inclined load, V is the vertical component of the inclined load. And one thing is mentioned, the original expression given by the Henson, this exponent was given 5. Okay. So, later on many researchers have observed that this is a very higher value. So, now they have suggested a lower value of this exponent, and that value is suggested that 223 for IQ and 324 for I gamma. Instead of using 5, you can use in any value in between 2 to 3. For IQ, you can use 2 also, you can use 2.5, you can use 3 also in case of IQ, or in case of I gamma you can use 3, 3.5 or 4. Okay, slightly lower value, but as the original equation is given 5. So, in my all the example problem I will use 5, but if in your question, if it is mentioned that you use this is the exponent value, that you have to use. If nothing is mentioned in the question, then you can use the 5 directly, okay, or you have to use the 5 directly. If nothing is mentioned, you use 5. If any value is mentioned within this given range, then you have to use that value. On in your design purpose, you can take any value in between the given range, or you can use the 5 also, but as it is suggested these ranges, so you can use this range. But my example problems I will use 5, and if nothing is mentioned in the assignment problem or the question exam question, you have to also use 5, but if any value is mentioned, then you have in the question, then that value you have to use. And note another important thing, that in case of eccentric loading, again like the Meharov, that one can use Hansen equation with B dash and L dash to compute the shape and inclination factor. So, remember that here, because different theory has suggested different approach to take care the eccentric loading effect. As in Meharov approach, what was the thing, that you use B dash and L dash to compute shape factor and depth factor. Okay. But in as per Hansen theory, that you use B dash and L dash to compute the shape factor and inclination factor, but for depth factor calculation, even if for eccentric loading you use B and L, not B dash and L dash. Okay. So, that is mentioned here, because in inclination there is A dash. So, that you can use as B dash L dash, but B and L to compute the depth factors. Okay. So, that means you have to use B and L to compute the depth factor as per the Hansen bearing capacity equation for eccentric loading, but to compute shape factor and inclination factor you have to use B dash and L dash or effective areas. But when in the third term of the equation you have to use B dash, okay, or L dash. Later on I will discuss why I have mentioned L dash, okay, because in Tazaki Meharov equation I am given only B dash, but here I have given B dash or L dash. Why is that? Why it is B dash or L dash? Because in Hansen equation there is a provision that you can incorporate the effect of horizontal loading direction also. What does it mean? That in Meharov equation the only angle is given. That means this load can act towards the width direction and towards the length direction also. For example, that if loading is acting parallel to the width, okay, horizontal load, because if inclined load has two components, but in a Meharov equation that angle is only given. So, you can calculate the angle and you can put it. So, there is no provision to incorporate that which direction the horizontal load is acting. Vertical load will always act vertically, but horizontal load will act horizontally, but there is a provision that it can act parallel to the length or it can act parallel to the base width also. So, that provision can be incorporated in Hansen's equation and basic also. So, remember that that is also advantages, that if you have a loading direction is specifically mentioned, then you can use the Hansen equation, you can use the basic equation, you can also use the Meharov equation, because if the vertical load and the horizontal load are given, you can calculate the resultant and you can calculate the angle on which the load is acting with the vertical, and you can use the Meharov equation. But in Hansen equation, that specifically if the horizontal load is parallel to length or parallel to width, that can be incorporated into the equation. So, that is why it is, if the loading is parallel to L, then we have to actually check both the conditions. That means taking B dash as well as L dash. So, I will explain this thing what I have discussed right now through an example problem. Then you will find that how this thing can be incorporated in Hansen's equation. So, that means this is the these things, the only difference is the depth factor. When you calculate, you put B and L, not B dash and L dash, but for other factors and the third term use the effective length or effective width or effective area in case of eccentric loading in Hansen's equation. Now, this is the basic bearing capacity theory, which is similar to the Hansen's bearing capacity theory. This is the again the general equation, but the NC value and NQ value we will get as per the Meharov equation. but again n gamma is different. So, this is the n gamma table. From here I will get the value of n gamma corresponding to different phi value, and this is the table by which is similar to the Henson's theory, but remember that in case of Henson's, if phi equal to 0, a particular equation is given, but here it is not given. So, that means if you use the Henson equation for phi equal to 0, then the table that is given. So, you have to use that table, then you have to use the equation which is given for phi equal to 0. But here in Henson and basic, you can see that type of equation is not given for phi equal to 0. It is a general equation where you can use these factors. So, that means SC value you can calculate by using this value. Then SC is 1 for strip footing, because for all the values safe factors are 1 for strip footing, and SQ we will get by using these equation, S gamma we will get by using these equation, and again S gamma should not be less than 0.6. Okay. And DC, because as there is no option for phi equal to 0 case, so it is a general equation for any phi, and that is similar to the Henson, that if phi for DC we can use by using these expression by for any phi, if two cases, one is if df by b less than equal to 1, another if df by b greater than equal to 1. Okay. And then dq I will get from these equation, and d gamma is 1 like Henson. But again when I calculate the when I calculate the these factors for eccentric loading, you can see, but here as per basic recommendation you use B and L when you calculate shape factor and depth factor both for eccentric loading. Okay. So, that means you have to use B and L, not B dash and L dash, to compute the shape factor and depth factor in case of eccentric loading in the basic bearing capacity equation. Remember that. Now, this is the inclination factor. So, this is phi equal to 0 case, and this is first one is the phi greater than 0 case, and then IQ I gamma. So, you can use by using these two equation. A dash is same as effective area, CA is same as 0.621 times the base cohesion CA value, and this is the phi is the friction angle, but M value you will calculate this by these conditions. So, again like Henson, here also if the horizontal component of the inclined load if parallel to B or L or both, that effect can be incorporated here. Okay. Now, M will be MB when H, horizontal component of the inclined load, is parallel to B. Okay. If it is parallel to width, then we will use these equation, M will be MB. Now, if it is parallel to L, then M will be ML. Okay. If it is parallel to both, then you have to calculate MA and ML and MB, then you use the MB square plus ML square to the power root. Okay. Then that will be the M. So, this clear. And another thing that again you use B and L, not B dash and L dash to compute M. Okay. So, that means in Henson's expressions, if you see the Henson's expression, that parallel to B or L case is not directly incorporated in these factors, not in the shape factor, depth factor, not in the inclination factor, it is mentioned H. Okay. So, that can be either horizontal parallel to B or parallel to L, but specifically it is not mentioned. So, later on I will explain how that effect can be incorporated. Okay. But in case of basic, that effect is incorporated in inclination factor determination. Okay, because when you calculate the m will be mb if h is parallel to b, m will be ml if h is parallel to l. If they are parallel to both, then I mean both HB and HL. HB means horizontal load parallel to B, HL means horizontal load parallel to L. Both are acting, then your M will be root over MB square plus ML square. I mean you have to calculate MB and ML and then you calculate the M. But again remember that when you calculate these things for eccentric loading, do not use B dash and L dash during calculation of M. Use B or L. So that thing is again this note is mentioned. You have to use B and L during calculation of M, not B dash but L dash, but you have to use effective area A dash. Okay, that will be effective area A dash during calculation of IQ and I gamma. So A dash will be the effective. So that means when you calculate depth factor and shape factor, as per basic use B and L. When you calculate M, use B and L, but when you use this A, you use the effective area. And in the third term of the equation, you use B dash. Okay? So you use B dash. So this is the difference. All these three cases, the three theories that I have discussed, that in the third term you have to use B dash, I mean effective for all the cases, but for Mehrab all the factors will be calculated by using B dash L dash, but basic I mean factors will be calculated considering B and L except the A, where you have to consider the A dash, and Henson you have to calculate all the factors by considering effective length or width or area except the depth factor. Clear? Okay. So now in the next class I will discuss the first IS method, because our IS code recommendation, what is our IS code recommendation, then I will solve a few example problems and the other effects like if the loading is inclined, if the loading is eccentric, or a compressibility effect in the bearing capacity equation. Thank you.